Welcome everyone for this VLSI design lecture series. In today's lecture, I'll be discussing about MOSFET scaling. The design of high density chips in metal oxide semiconductors VLSI technology requires that the packing density of MOSFETs used in the circuit is as high as possible. And consequently, the sizes of the transistors are as small as possible. The name itself indicates very large scale integration. The name itself indicates that the size of the transistor should be as small as possible so that more number of transistors can be infused in an integrated circuit. The reduction of size, which is the dimension of MOSFET, is commonly referred as scaling. The reduction of size is normally referred as scaling. It is expected that the operational characteristics of MOSFET will also change with the reduction of its dimensions. There are two basic types of size reduction strategies which are normally followed. The first one is called as full scaling, which is also known as constant field scaling. The second one is called as constant voltage scaling. So the scaling of the MOS transistors are concerned with systematic reduction of overall dimensions of the devices. The proportional scaling of all the devices in a circuit would certainly result in reduction of total silicon area occupied by the circuit. And ultimately, the size of the entire integrated circuit starts to reduce, or the area of the integrated circuit starts to reduce. To describe this device scaling, normally we use constant scaling factor called as S. S greater than 1. S means capital S always indicates scaling factor. All the horizontal as well as vertical dimensions of large size transistors are divided by this particular scaling factor to obtain the scaled devices. Let us have a look at a basic structure of a MOSFET, which consists of 3 terminals: gate terminal, source terminal, as well as drain terminal. Let us consider L to be the length of the channel, W to be the width of the channel, TOX to be the thickness of the oxide, and N to be the doping level concentration of substrate and drain as well as source. Whenever we apply scaling factors, the following things will happen. The channel length gets scaled by a factor called as S. So the new channel length will be represented by L dash. So L dash will be equal to L divided by S, where L dash is the new channel length after scaling down. Capital L is the length of the channel, that is the distance between the source and the drain terminals. S is nothing but the factor of scaling or scaling factor. Similarly, the width of the MOSFET can also be scaled. W dash is nothing but the width of the MOSFET obtained after scaling. W is nothing but the original width. S is nothing but scaling factor. So W dash is equal to W divided by S. Similarly, the oxide thickness. The scaled oxide thickness TOX dash is given by TOX divided by S. So when all these factors are scaled down, similarly, the doping level concentrations will also change. With respect to the substrate, doping level concentration, new doping level concentration will be equal to Na into S. With respect to source as well as drain, the new doping level concentration will be equal to Nd into S. Here, for doping level concentration, the scaling factor will be multiplied. As the size, thickness, length, and width are getting reduced by a scaling factor called as S, more number of doping level concentration or more number of dopants should be added so that the device operates properly. Hence, the doping level concentrations, the scaling factors will be multiplied. For the new scaled down doping level concentration, the scaling factor will be multiplied because all other factors, width as well as length as well as thickness, are getting reduced by scaling factor called as S. To maintain same operational characteristics, more number of doping level concentrations have to be added, or more number of dopants have to be added for drain source as well as substrate terminals. Hence, the scaling factor will be multiplied by the doping level concentration to obtain new doping level concentration, scaled doping level concentration. Here I'm named what these W, L, TOX and N means. L means the length of the channel, W means the width of the MOSFET, TOX is nothing but thickness of the oxide, and N is nothing but doping level concentration. As I told you, this full scaling, which is also called as constant field scaling, this particular scaling attempts to preserve the magnitude of internal electric fields in the MOSFET, while the dimensions are scaled down by a factor of S. To achieve this goal, all potentials or voltages must be scaled down proportionally by the same scaling factor called as S. We have to note that this voltage scaling also affects the threshold voltage, whether it might be an NMOS transistor or it might be a PMOS transistor. All the voltages will be affected, including threshold voltage. So this particular table indicates the quantity, what is the quantity before scaling and what will happen after scaling. When it comes to channel length, before scaling, we represent channel length as capital L. After scaling, so channel length, the new channel length which is obtained, L dash, will be equal to L divided by S, where this L dash is the new channel length which is obtained after scaling. Capital L is nothing but channel length, the old channel length. S is nothing but scaling factor. Similarly, channel width. So before scaling, the channel width is represented as W. After scaling, we use W dash, which is equal to W by S. W dash is nothing but new width which is obtained after scaling. Capital W is nothing but the previous olden width of the MOSFET before scaling, and S is nothing but the scaling factor. Similarly, gate oxide thickness, TOX, will be equal to TOX is the gate oxide thickness before scaling. TOX dash is the gate oxide thickness after scaling, which is given as TOX divided by S, where TOX is the thickness of the oxide before scaling and S is nothing but scaling factor. As I told you previously, when we employ this particular full scaling, even the voltages, including threshold voltage, will change. Power supply voltage, before scaling, we consider as VDD. After scaling, VDD dash is equal to VDD divided by S. Threshold voltage, VT naught, which is the threshold voltage before scaling. VT naught dash is equal to VT naught divided by S, which is after scaling. Doping densities with respect to the substrate and the drain as well as source will be affected in this way. Before scaling, we represent it as Na and Nd, whereas after scaling, we represent it as Na dash is equal to Na multiplied by S. Nd dash is equal to Nd multiplied by S, where S is nothing but scaling factor. As I told you previously, the reason why we multiply the scaling factor with respect to this doping densities is, as we reduce all these voltage quantities as well as other dimensions of the MOSFET, to make sure that the MOSFET operates with the same characteristics as the previous one, we have to increase the doping level concentration. Hence, the scaling factor will be multiplied with doping densities. So this particular table clearly indicates or clearly shows us how the doping level quantities will be getting affected. In addition to this dimensions, length such as length, width, gate oxide thickness, VDD, VT naught, doping concentration, we have other quantity as well called as current. So we have to analyze how this current also gets affected. Now let us consider the influence of this full scaling described here upon the current voltage characteristics of MOSFET as well. We will be assuming that the surface mobility mu n or mu p is not significantly affected by scaled doping densities. The gate capacitance per unit area is changed as follows. COX dash, which is the new gate oxide capacitance after scaling, will be equal to epsilon OX divided by TOX dash, which is equal to epsilon OX divided by TOX divided by S, where TOX divided by S, this S is nothing but scaling factor. Instead of representing it as TOX dash, we have represented it as TOX divided by S. I'll shift this S towards the numerator, so it goes to the numerator, S into epsilon OX divided by TOX. We already are familiar what is meant by this epsilon OX divided by TOX. That is nothing but capacitance, COX, oxide capacitance. So new scaled gate oxide capacitance COX dash will be equal to S into COX, where COX dash is the new obtained gate oxide capacitance, S is the scaling factor, COX is nothing but the olden oxide capacitance. So this is how the oxide or capacitance will vary. In addition to this, let us also focus upon current. Let us consider drain to source current under linear region. We are already familiar with this particular expression for drain to source current under linear region of operation. IDS linear is equal to COX into mu into W divided by L multiplied by VGS minus VT into VDS minus VDS square divided by 2. I'll consider that as equation number 1, where IDS is nothing but the current with respect to drain to source. COX is the oxide capacitance. Mu is the mobility of electrons or holes. If we consider N-channel MOSFET, mu will be mobility of electrons. If we consider P-channel MOSFET, mu will be mobility of holes. W is the width of the MOSFET. L is the length of the channel. VGS is the gate to source voltage. VT is the threshold voltage. VDS is the drain to source voltage which we have applied. So this particular equation was dealt in our previous sessions when we derived expression for drain to source voltage, drain to source current under various regions of operations such as cutoff region, linear region, as well as saturation region. For the sake of explanation here, we have considered linear region of operation. So IDS is equal to COX mu W by L into VGS minus VT into VDS minus VDS square divided by 2. I'll be considering that as equation number 1. Now let us scale this particular drain to source current which is present in the linear region. We can write it as IDS dash linear is equal to COX dash, which is the scaled oxide capacitance, into mu. As I told you previously, we assume that the mobility is not changing, into W dash, which is the scaled width, divided by L dash, which is the scaled length or channel length, VGS dash minus VT dash into VDS dash minus VDS square dash divided by 2. So what we have done is we have considered the scaled drain to source current. Now IDS dash linear can be written as, in place of COX dash, I can represent it as S into COX, because COX dash is equal to S into COX, where S is nothing but scaling factor, COX is nothing but gate oxide capacitance, into mu, into, in place of W dash, I can write it as W divided by S. In place of L dash, I can represent it as L divided by S. I'll represent the same equation even here. S and S gets cancelled, and we will be arriving at this particular equation. IDS dash linear will be equal to S into COX into mu into W divided by L, into VGS dash can be expressed as VGS divided by S, minus VT dash can be represented as VT divided by S, into VDS dash can be represented as VDS divided by S minus VDS divided by S the whole square divided by 2. So what we have done here is we have applied the scaling formulas, whatever we have seen previously. So once we reshuffle the equation, we'll get IDS dash linear is equal to S into COX into mu into W divided by L into, I'll be taking 1 by S square as common in this entire equation. So once I take 1 by S square as common in this entire equation, I'll be left out with 1 by S square into VGS minus VT into VDS minus VDS square divided by 2. The square and this S gets cancelled. So we'll be arriving at this particular equation. IDS dash linear will be equal to 1 divided by S into COX into mu into W divided by L multiplied by VGS minus VT into VDS minus VDS square divided by 2. I'll consider that as equation number 2. Now, if we apply equation number 1 in equation number 2, if we just apply equation number 1 in equation number 2, this is equation number 1. If I apply this equation number 1 in equation number 2, I'll be getting IDS dash linear is equal to IDS linear divided by S. That is, the scaled drain to source current in linear region is equal to IDS in linear region divided by scaling factor. I'll consider that as equation number 3. So this particular equation holds good for the drain to source current which is scaled under linear region of operation. Next. Similarly, the drain to source current in saturation region can also be written as follows, which will also be scaled down by a factor called as S. ID saturation dash will be equal to ID saturation divided by S. That is, the scaled drain to source current under saturation region will be equal to the normal drain to source current under saturation region divided by the scaling factor. Let us consider that as equation number 4. Now, up till now, if we just recall or brush up the concepts, we have found out how this scaling factor actually works. We have scaled down the length, width, oxide thickness, gate oxide capacitance, as well as doping level concentration, drain to source current in linear region as well as saturation region. So once the voltage as well as current changes, definitely the power dissipation or power will also change. So let us see how this power gets affected when it is scaled. We already know that the generalized equation of power is given by the formula P is equal to V into I, voltage multiplied by current. With respect to our Mosfet, let us consider this particular equation. Power will be equal to drain to source voltage multiplied by drain to source current. So P dash will be equal to, which is the scaled power will be equal to VDS dash into IDS dash. P dash will be equal to VDS dash is nothing but VDS divided by S. IDS dash is nothing but IDS divided by S. So I'll write the equation as P dash is equal to 1 by S square into VDS into IDS. I'll take this as equation number 6. Now, VDS into IDS is nothing but power. Here we have written VDS into IDS is nothing but power. So once I substitute equation number 5 and equation number 6, that is power in place of this VDS into IDS, I can write the equation as P dash is equal to 1 by S square. I'll write it as it is in place of VDS into IDS, because VDS into IDS is nothing but normal power for Mosfet. So I'll write it as power, which is unscaled power. So P dash will be equal to P divided by S square. That is, the scaled power will be equal to the normal power divided by S square, where S is nothing but scaling factor. If we observe, the scaled power is equal to normal power, unscaled power divided by square times of scaling factor. So these are how the different quantities gets affected when we scale down the MOSFETs. I hope that you have understood. Thank you.